even quicker now. So thanks again for having me today. So I'm Angelo Ferrando from the University of Genova. Today I'm going to sum up already the summarizing of recent work that we published in a journal called TOSEM, so Transactional Software Engineering Methodologies. This work is about formal verification of multi-agent systems. Specifically, the problem is that we want to do static formal verification, such as model checking of these systems, but they might become very big, very complex, and might have like state space explosions. So one possibility is to try to tackle this kind of problems is by trying to reduce this complexity by adding some kind of assumptions in our abstraction of the model of the system that we are used for doing static verification. But this might bring us to problems like having some kind of imprecise or incomplete abstraction, which invalidate practically our results in the formal verification stage. So practically what we can have is that the environment matches the model. So in that case, it means that our abstraction still works and the verification is correct, or the environment, unfortunately, now with this assumption fall outside the system. And in this case, we cannot actually guarantee that the system is always going to behave correctly. So what we propose in this journal is an extension of a previous work where we combine two formal verification techniques, so static model checking and runtime verification, in order to validate these assumptions at runtime after we did the formal verification step. So this practically is based on the notion of unstructured abstraction. So when we say unstructured abstraction, we mean that we model our system without actually giving any kind of assumption with it. So we try to formalize the system as precise as possible, but this may be in cases, for instance, in multi-agent system or in distributed system in general, this may bring us to some kind of state space explosion problem, because we might have a lot of states, a lot of transitions. So what we instead are interested in doing these more realistic scenarios is structured abstraction, where instead of just modeling the system as it is, we try to abstract away some details that are not important, and we do that from assumptions. So the assumptions must be correct, otherwise the model is imprecise and the verification process is we cannot trust it practically. So what we do is we try to use to combine these formal verification techniques, such runtime verification, in order to help us with this. So the proposal consists very quickly in modeling the structure abstraction using a domain-specific language that we presented in the paper called EAASL, transforming this specification into a middle layer specification called test expression, which is the one that we are going to use both for representing our assumption in the model for model checking, and also later on for automatically synthesizing runtime monitors to validate our assumptions at runtime while the system is running. We also tested and ran our system, so we implemented it, and we tested it on top of MCAPL framework, so the model checking framework for model checking multi-agent systems in Java and Gwendolyn. So this is just an overview of the approach. I'm just going to say something about it. So practically we start in the top right from our domain-specific language that I'm going to show to you later on. From this specific language, we translate it to a trace expression, which is this formalism, which is used for runtime verification. But in this work, we also showed how we can translate this specification into the Java abstract environment, which is used in Agent Java Pathfinder model checker to do the verification process. So we first start with the specification, we create our abstract environment, we do our model checking, and then we use the same specification to generate a monitor which will be deployed at runtime to check and validate that our assumptions are actually consistent with the actual environment. So this is just an example. In the paper, we present this as a toy example, but we also present in a robotic scenario the same use with the Curiosity rover, at least with a simulation of the Curiosity rover. So in this case, we have an intelligent cruise control. So an agent is controlling a car, an autonomous car, and we have in our abstraction, we have different kind of proposition that represent the state of the car. So for instance, if it is safe or not to accelerate, if we reached or not the speed limit, if the driver is braking, if the driver is accelerating, and stuff like that. And if we consider the notion of abstract unstructured and structured abstraction. In the case of unstructured abstraction, we would have that we might generate all the possible subset of these propositions when we generate our abstract model. So what we do instead, we try to put some kind of requirements, and this is just a snippet of an example of our domain-specific language that present in this paper. So here we define what is our agent, so the agent car, what are the beliefs that are involved in this scenario, what are the actions, and then we can, the most important part, we can list the constraints on these beliefs and actions with respect to these agents. So for instance, we could say we have when before encodes constraints. So here we have, for instance, we can say when the car believes that the driver accelerates, then it also believes something else, like that it's safe to accelerate, or the car believes that the driver accelerates always before believing that it reached it at speed limit. These constraints, even though they seem very simple, they allows us to practically prune states from our abstract environment and helps us to speed up the model checking step. So from this specification, we automatically synthesize the test expression, which is the monitor. And this is just for showing you that why we actually come up with a domain-specific language, because in a previous paper we presented this approach with less possible constraints. It was with less power, but we presented this specification. So you could imagine that you need to describe this monitor and then use the specification to generate the abstract model and the monitor. But as you can see, it's not very user-friendly with respect to the previous one. So this one is the new one. So we start from this and this is automatically compiled by our implementation to this. And this is what is going to be used for generating the runtime monitor and the abstract environment in Java. So just to give you an hint on the experimental results that we got, for instance, in this case, when we ran our system, so we did our verification statically with model checking, and we did our validation with anti-verification. We didn't get anything, for instance, in that example. But in order to test it, we also modified the program, for instance, by letting the driver, for instance, to accelerate also when it's not safe to do so. So this is a violation of what was our first constraint, if you remember in the previous slide. So we did the formal verification, so the model checking, and it passed. So all the LTL properties that we wanted to check were validated. Were verified. And then at runtime, we used the same specification to generate a monitor that reported the error that I just showed here. So for instance, in this case, we can see that when the driver does actually that is a violation of our assumption, and this is reported by the monitor, and this can be used to, for instance, update the model or knowing that our verification process is not to be trusted because our assumptions are violated. And this might be a problem or on our side, so we did some wrong assumption, or on the implementation side, which is not satisfying our assumptions, what we had in mind at the end of the day. So by concluding very quickly, you can find, I hope that you're going to read the paper. There is a lot of more technical details. So in particular, what we presented was a unified approach to combine formal static verification and runtime verification in the context of multi-agent systems. Everything is implemented and explained in the paper. And this is very nice from the point of view of validation in order to practically try to reduce the reality gap between formal verification with abstraction and the actual implementation. For future work, we are planning to express a greater range of constraints. So the three kind of constraints that I explained to you, that are the ones that we use in the paper, but we are planning to use more of them. And we also are planning to apply to more case studies, because one is to example with the cruise control, and we also presented one with the robotic scenario with a simulation of the Curiosity rover, but we're also planning to have applied to more of them. So that was it. Sorry for maybe too fast, but thanks again for having me.